In an equation, for example, x squared plus 2x minus 3 equal to 0, we are seeking an unknown number x. In a differential equation, we are seeking an unknown function. And let's call that function y of x. We could also call it f of x. So let's say, for example, we are seeking the function satisfying this equation. Or we could also involve derivatives. For example, if we take the second derivative of y minus the first derivative of y and see when that's equal to the function itself. These two are called differential equations. So here we are seeking an unknown function, not an unknown number, but an unknown function. Let's take a simple example. Let's say we are seeking a function y that satisfies this equation. That is, that the derivative of y should be equal to 10x. In this case, it's easy to see what the solutions must be, because here we have that the derivative of a function is equal to 10x. That means that the antiderivative, which is in this case is just y of x, must equal to 5x squared. Since we take the derivative of this one, 2 comes down, and get 10x. And also here we could have a constant. So the solutions to this equation is just this function here. If we instead consider this differential equation, we are seeking a function which derivative is equal to the function itself. If we know about exponential functions, we know that if you take the derivative of that, that's just equal to itself. So this is the solution to this one. But could there be more solutions? Well, obviously, if we take a constant times e to the power of x, this will also be a solution. Because if we take the derivative of this one, the constant just comes along, and the derivative of this is just this. So also in this case, the derivative is equal to itself. So these are equal, and that means that they satisfy this equation. But can there be still more solutions than this? We will prove that it cannot be. To show that, let us rewrite this equation. We subtract y of x on both sides, and then we get this instead. Let's say we have found a solution to this equation. Then we have also found a solution to this equation. Why is that? Well, obviously, if this is equal to 0, then this must also be equal to 0, since this is equal to 0. So we have that if we have a solution to this equation, then it must also be a solution to this equation. We can also go the other way. If we have found a solution to this one, that means that the product of this one and this one is 0 for all x. Since this is never 0, that means that this must be 0. And then we have this situation. So the arrow also goes in the other direction. So these two equations are equivalent, meaning that they have the same solutions. So instead of solving that one, we can just as well solve this one. Multiplying in this, we get this one here. Now, this left-hand side we can rewrite in the following way. Like this. And the reason for that is that if you take here now, here's the derivative of a product of two functions. And if you do this, you will end up with the left-hand side here. Because here you first need to take the derivative of y, and this one. Then you just multiply with this one. Then you take plus. Then you take this one without doing anything. And then you take the derivative of this one. And this is a composition. If you take the outer derivative, you just get this one. But you also get the inner derivative of minus 1, which makes this plus a minus here instead. So this here, left hand side, is same as this one. So that means we can solve this one. And here we have that the function have a derivative that is equal to 0 for all x. But that just means that this function here must be a constant function. And now we can multiply by e to the power x on both sides. And then we get this. And here, this is just equal to this, which is equal to e to the raised to the power of 0, which is just 1. So we are left with y on this side. Then we see that y must be equal to this. But that means that if you have this equation, the solutions to that equation must be this. So this is the only possible solutions to this equation. And that's what we already said. So here we have all the solutions to this equation. The result we just found we can state in the theorem. We can also generalize the theorem directly. So for example, if you have a differential equation looking like this, that is, if you have the derivative of a function should be equal to a constant times the function, then we can show, just reasoning in a similar way to we just did, that the general solution to this is this one here, where c is just some arbitrary constant. Let's consider the same equation as we just solved algebraically, but let us now instead solve it graphically. Assume that an initial condition for this one is y0 should be equal to 1. This equation here tells us that if we have found a solution, then the derivative should be twice as large as the function itself at every point x. That means that for x equal to 0, we should have the derivative at that point should be twice as large, so it should be 2. For x equal to 0, then the graph should be at 1, so it should be here. And this means that the slope at this point should be 2. So we see that if we would have gone one step in this direction, we should go 2 up, then we would have ended up here. So if the graph would have continued with the same slope as it had here, in a straight line, then we would have ended up here after one step. Of course, we don't know if the solution is a straight line, but if it would have been. So if we take this as an approximation of our solution, it means that if we go one step here, we should end up here. If we now instead start here, that means that if we put in 1 into y, then we should be at 3. Then according to this, if it should be a solution to this one, then the derivative must be twice as large as this one. So that means that at this point, the derivative should be twice that, so it should be 6. And here we have drawn this, because if you go one step here now, you go 6 up, you end up here. So this is the continuation of the curve if it will continue with this slope. So you see that we can trace out an approximate solution by going in steps of 1. And here we have drawn it again, this blue curve here, and this is an approximate solution. But instead of going a step of 1, we could also go in step of a half. So if we will continue in step of a half, that means after half a step, and if we start with this slope, 2, we should go up 1 from this, so we should end at 2. And that's what we have drawn here instead. For the red dot here is, if you go half a step from this point, you go 1 up, and then you end up at 2. And if you continue this way, going half steps, you would have ended up with this red graph instead. So this red graph here is an approximate solution if you go half steps. And half steps give you better approximation. Then you could of course go quarter steps and 10 steps and so on. If you go infinitely short steps, then you would end up with this one here. And this is just the algebraic solution. So you see that for shorter and shorter steps, you come closer and closer with your approximation to the algebraic solution. So these are graphic solutions with varying degree of accuracy depending on how far you go in each step. So this is solving the differential equation graphically.